stream works first. Hello. Just checking that the stream works first. Everything's all right. Alright, I'll get started in just a minute here. At 2:03 I'll get started. Alright, I'll get started in just a minute here. At 2:03 I'll get started. I'll get started in just a minute here. At 2:03 I'll get started. I'll get started in just Okay, so I'll get started now. Welcome to the MATH3411 workshop. This will be part 1 of 2 parts. There'll be another session on Wednesday. My name is Jay, and I'll be going through topics 1 and 2. And then after I'm done, Steve will come on and do topic 3 for part 1. So in topics 1 and 2, it will be introduction to code and ciphers. Firstly, going through some, prerequisites as to what they suggest you know in this course before getting started. And then looking at ASCII code and ISBN code. And then topic 2, we'll go through error detection and correction. It will be like the longer topic out of the 2. And we'll be looking firstly at binary repetition codes, and then binary hamming, and then in general T-error correction codes, and then finally linear codes. Okay, so let's get started. Firstly, we have an overview of the first topic, or I guess this is an overview for the entire course in general. The entire course in general will just be about encoding and decoding messages, as well as taking into account noise that can happen between the transmission of a sent message and received message. And this noise can cause information that was intended to be sent to be corrupted. And we'll go through some methods on how to deal with that throughout this course. Okay. So firstly, a first definition is the source alphabet. A source alphabet is just defined as a set, for example, S1, S2, S3, all the way to SQ, with associated probabilities of P1, P2, P3, all the way to PQ. And intuitively, this is just like our English alphabet. It's the characters that we use to compose the message that we want to say, basically, right? So if you want to say anything in the English alphabet, like let's say I want apples, you constructed the message I want apples out of the letters that come from the 26 letters of the alphabet. Okay, that essentially is what the source alphabet is. And the reason why this associated probabilities is also the same, intuition as how in the English alphabet not every single letter is used equally likely. Like, for example, the vowels may be used a lot more frequently than other letters. Okay. Another definition that we have is the code alphabet. A code alphabet is also defined as just a set, usually denoted by capital C, and can be C1, C2, C3, all the way to CR. Okay. So we have a source alphabet, let's say A, B, C, and a code alphabet, let's say 0 and 1, so the binary numbers 0 and 1. And suppose we have the following encoding, right? So we can encode A by the number 0, encode B by the number 10, and encode C by the string of numbers 1, 1. Then we can encode the message A, B, B, C as 0, and then 1, 0, and then 1, 0, and then 1, 1. Essentially, the source alphabet is like the English alphabet again, like A, B, C is how we humans construct messages. The code alphabet would be what I guess the computer sees, right? So it's like the computer only see binary numbers, and in that sense, when you want to construct a message like I want apples, they will pick out the binary code for I, the binary code for W, the binary code for A, and so on, and construct a string of numbers. Okay. All right. Next, some prerequisites. Most of you would have probably come across modular arithmetic and probability in your first and second year courses, most likely in discrete maths. And here are just some basic facts about modular arithmetic. There won't be any examples or questions going on on this. But we'll come back to see a lot more of modular arithmetic in chapter 5. But all throughout this course as well, you will see, I guess, modulo be used. Okay. Another topic that will be quite frequently coming up would be probability. The only distribution you'll probably need to know is binomial distribution. And I guess Bayes' rules of the conditional probability and law of total probability, you probably need to know some of those as well. All right, let's move on to our first piece of content then. The first code that you're kind of introduced to in this course is the ASCII code. And here we define the 7-bit ASCII code. The 7-bit ASCII code is a code where each symbol is encoded as a string of exactly 7 bits, where each bit is either a 0 or 1. Okay. So for example, that's just saying, like, let's say you have 1, 0, 1, 1, 1, 0, 0. This here could be an ASCII code. Okay. And it could denote something. It could denote some symbol. All right. So this is our code word. And for example, it might denote the symbol star. Okay. It could be anything. Yeah. So you basically have a symbol, and then you have a string of 7 numbers, either being 0 or 1s, and that forms a code word that denotes that symbol. Okay. All right. Next, we also have the extended ASCII code, which is the same as the 7-bit ASCII code, except there's an extra bit at the front that acts as a check bit, requiring the number of 1s to be even. Now, if you get back to our example before just then, let's say we have star equals to 101110, okay? And let's say we're transmitting this code word 101110 over to a receiver. But between the sending and the receiving, there's some noise that causes, let's say, the last bit here, this one, to turn into a 1. Okay, so there's a bit of corruption there, right? And so the point of having this extra check bit is to ensure that we can detect when there is an error. Okay, so by this extended ASCII code, by adding on that extra bit at the front, we can now deduce whether there's an error. So for example, the 7-bit ASCII code for the symbol A may be denoted as 0110010. And the extended ASCII code for A would become 10110010. Why do we know that this front bit must be a 1? Well, we want to have this front bit ensure that there's an even number of 1s in the code word. So at the moment, there's only 3 1s in the code word. And so we want to add on an extra 1 to ensure that there are in total 4, which is even, right? 4 1s in the code word. Okay. Again, what's the benefit of this? Well, for example, let's say the symbol, the 7-bit ASCII code for symbol A gets corrupted. So it becomes a 0, 1, 1, 0, or like I'll write out properly. This gets corrupted and becomes 0, 1, 1, 0, 0, 1, 1. Okay? So rather than having this last bit be a 0, it got corrupted into a 1. Now having the extra bit in the front be a check bit will help us figure out that there's an error here, right? Because this check bit ensured that there were 4 1s in our code word. But now, since this last zero got corrupted into a 1, there are now 5 1s in this code word, which should indicate to us that there's an error. Because remember, the check bit should ensure that we always have an even number of 1s. And so clearly, since there's 5 1s in this corrupted code word or this sent code word, we know that an error must have occurred. Okay. Okay. Not sure why this is like this. Yeah, not sure what happened to this slide, but essentially this is what I was saying earlier. This is a new slide. I'm not sure what happened to this slide, but this slide should be about ASCII burst code. I'll just write it up here. Yep, so the 8-bit ASCII burst code is just like the extended ASCII, but with an extra row at the bottom called ETB, which acts as a further checking mechanism. In this case, it will act as a check code word, requiring the number of 1s in any column to be even as well. So I don't know why the example jumped to the top. It should have been down here. But essentially, let's say you want to send the message 101. No, sorry. You want to send the message, I don't know, let's say this is A, B, C. Okay. And the 7-bit ASCII for A, suppose, is this. The 7-bit ASCII for B, suppose, is this. And the 7-bit ASCII for C, suppose, is this. Okay. Then firstly, we extend the 7-bit ASCII into 8-bit ASCII by adding on check bits at the front to ensure that in each row here, there are an even number of 1s. So in the A here, there used to be 3 1s, and now there's 4 1s if you add this one on. In B, there was already 2 1s, and so we don't have to add anything on. And for C, there was only 1 1, and so we add on 1 1 to get 2 1s. Okay. But on top of that, we also look at it column-wise. Okay. So in each column, we also want to ensure that there are an even number of 1s. So for example, here, there's now 4 1s. For example, here, we don't have to do anything because there's already 2 1s. For example, here, there's only 1 1, so we put an extra 1 in to get 2 1s, and so on. Okay? Now, this adds an extra level of, I guess, detection and error correction, because when you send this message now, this block of messages here, or this block of code words here, these extra check bits on the left and on the bottom will help you determine, I guess, if there's an error and where's the error. Okay? So for example, let's suppose that this here became a 1. Okay? All right, so as we sent this, like these 3 code words across, this one got corrupted and the 0 here got changed to a 1. Well, firstly, we would know that there's an error in this row. Maybe I'll use a different color here. Okay, I'll use orange. So I would, right now, immediately know that there's an error in this row. Why do I know there's an error in this row? Because we have 3 1s, right? So there's a non-even, or like, in other words, an odd number of 1s, okay? And furthermore, I would also know that there's an error in this column. Why is that? Well, again, we should have an even number of 1s in every row in every column. Here, we have a odd number of 1s in this column. And so, by looking at the number of 1s in the row and the columns, we have deduced that there must be an error exactly here, right? The intersection between this column and this row. Okay, so the 8-bit ASCII burst code now allows us to not only detect there being an error, we can also correct we can also correct an error. Okay, but the caveat here is that we can't always correct it, right? Like for example, if let's say this changed to a 1 as well. Oops, I should use red. Be consistent. Let me change back to red. Suppose that this also changed to a 1, right? Then I know that there's an error in this column and this column, but I won't know what row the error is in because every row will still have an even number of 1s. Okay, so that's kind of like the fault of these ASCII codes and these extended ASCII versions of codes. They're very restrictive, right? You can only really detect and correct single errors. Okay. All right, moving on. Another code that we have is the ISBN code. An ISBN number is a code word used to uniquely denote books usually. They have 10 bits, with its last bit being a check bit requiring the following condition. The summation of all 10 of these bits. Okay, this is actually a typo, I believe. There should be an extra I here. Okay, so each of these check bits, weighted by the position of where they are, summed up all together, should be congruent to 0 mod 11. Okay, so an example here is 0387978127 is a valid ISBN code, whereas 1118231331 is a not valid ISBN. Okay, so for example, why is this a valid ISBN? Well, it just means that the summation from 1 to 10 of I times each xi ended up being congruent to 0 mod 11. Yeah? So in this case, for this number, that would have been the same as 1 times 0 plus 2 times 3 plus 3 times 8 plus 4 times 7 plus 5 times 9, blah, 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 all the way until 10 times 7. Okay? So essentially we took 1 times 0, 2 times 3, 3 times 8, 4 times 7, 5 times 9, blah, 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 all the way to 10 times 7. Okay? And this ended up equaling to something that was divisible by 11. On the other hand, this number here would not be a valid ISBN because when you did the same sort of calculation with this number, it ended up with a number that wasn't divisible by 11. Okay? All right, we'll go through an example that goes through this in a bit more detail. Okay, but firstly, in theorem, the ISBN 10 code has error detection abilities up to a wrong digit and the interchanging of 2 digits, right? So if there's clearly the first one's obvious, right? If you have an ISBN code and suppose one of the digits are wrong, then obviously that will change the sum you get. And if you change the sum you get, you will no longer be divisible by 11. And furthermore, another error can detect this, the interchanging of 2 digits. Again, same reasoning. If you have a string of digits and you take 2 distinct digits and swap their positions, obviously you'll get a different sum, which will cause it to no longer be divisible by 11. Okay? So an example, check whether the sequence 09091170064 is a valid ISBN. So to do this, we just have to look at the summation from I equals 1 to 10 of I times each of the xi. So we're weighting each of these digits by their positions. And that would give us 1 times 0 plus 2 times 9 plus 3 times 0 plus 4 times 9 plus 5 times 1, blah, 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 all the way until we get to 10 times 4. Okay? Let's go ahead and calculate what this is equal to. We get 1 times 0 plus 2 times 9. Let's do this quickly in the calculator. Okay, and we end up with 208. Okay, now 208, you can check in a calculator, but this would not be congruent to 0 or 11. In other words, this number is not divisible by 11. Okay, so clearly this ISBN code, or like this code here, is not a valid ISBN code, right? So thus 09091170064 is not a valid ISBN. Okay. Yeah. Now you might ask, okay, sure, it's not a valid ISBN, but if you wanted to make it a valid ISBN, what do we need to change? Well, for example, if you wanted to change the check bit at the end here, what check bit must we change it to such that it becomes a valid ISBN? All right, so I'll write this here. So if we were to alter the check bit to become a valid ISBN, what would we change it to? Change it to. Okay. Well, to figure that out, it's not too difficult. So essentially, you want to look at the sum of the first 9 terms first, in which case it would be the same as 208. It's the sum of all 10 terms. So the first 9 terms, oops, I don't know why I had an extra L there. First 9 terms, sum to, where sum to 208 minus 10 times 4, which is 168. Right. Okay. Now we know that we need this last check bit to be a number between 0 and 9, such that we have 168 plus 10 times this last digit is going to be divisible by 11, right? We need this to be mod 11 and be congruent to 0, okay? To do this, you can just do trial and error on your calculator. Right? For example, 168 plus 10, is that divisible by 11? No. 168 plus 20, is that divisible by 11? No. 168 plus 30, is that divisible by 11? Yes. Okay. So we found out that 168 plus 10 times 3 is indeed congruent to 0 mod 11. And so if we did want to make this ISBN, or this code here, a valid ISBN code, we need this last digit to be a 3 instead of a 4. Okay? All right. I'll move on then. So moving on from topic 1, right? Topic 1 was very brief, just an introduction to code and ciphers, as well easing you into 2 of the more basic codes like ASCII code and ISBN code. And now we'll move on to topic 2, which is error detection and correction, and we'll be introduced to more complex codes and more general codes, as well as their detection capabilities and their error correction capabilities as well. Okay. So an overview of this topic. This topic will in particular focus on the noise that I talked about earlier. Okay. We look into the ability of certain codes, so I guess better codes that can detect and correct errors that are formed due to this noise. An example of how the noise might look like would be, suppose you're trying to send 0, you have a success rate of 1 minus p that will actually send it to 0. But there's also simultaneously some noise in here, so there's some noise in this process here, right? That might cause a 0 to be sent to a 1. Right? So there's a p chance of corrupting the 0 to 1. Vice versa, similarly for the 1, right? the 1 has a success rate of getting back to p of 1 minus p, and there's a p probability chance of it being corrupted to a 0. Okay, so the possibility of corruption is caused by this noise. Okay, so the 8-bit ASCII burst code, the ISBN 10 code, were examples that we looked at just in topic 1 that introduces us to this idea of being able to detect and correct errors, right? So the whole point of extending 7-bit ASCII to the extended 7-bit ASCII and then to the 8-bit ASCII burst code was so that we could better detect and correct potential errors. Similarly, for the ISBN 10 code, the point of having a check bit at the end to make sure that the sum is divisible by 11 is again to detect errors and to try to correct them. Okay. In this, like I said, in this topic, we'll look at more complex and general codes that also have detection and error correction capabilities. Okay. Firstly, introducing you guys to an idea called information rate and redundancy. This is a form of metric that kind of measures how good a code is, okay, or how efficient a code is. So it's defined by and denoted by R, and it's defined as the number of information digits over the total number of digits. And in particular, for the set of radix R code words, C, it is the same as log R of the cardinality of C over the length of the code. Okay. So firstly, you guys might be wondering what radix R means. It basically just means what the numbers can be, like what the digits can be. Right. So far we've only looked at binary, right? Every single code that we saw previously, or I guess not ISBN, because this has, I guess, can go all the way up to, from 0 to 9. So I guess this is a mod 10 code, right? This is code where the symbols come from mod 10, or come from, yeah, the integers mod 10. But for example, the ASCII code was binary, right? It can only be 0 or 1s. Yeah. And so radix just means integers mod what. Okay. So for example, radix 2 means it's binary. You can use the numbers 0 or 1, the digits 0 or 1. Radix 3 means you can use the digits 0, 1, or 2. Radix 5 means you can use the digits 0, 1, 2, 3, 4. Okay, that's what radix means. Okay. All right. So let's give a bit more intuition into what R actually represents. For example, consider the 8-bit ASCII, so the extended ASCII code. Okay. The information rate of the extended ASCII code would be 7 on 8. This is for the 8-bit ASCII R. Okay, so the 8-bit ASCII's information rate is 7 on 8. Why is that? Well, the length of the code is composed of 8 bits, right? But the first digit or the first bit in this 8 bits is used as just a check bit, right? It doesn't convey any information. It's only there to ensure that we can have some level of detection of errors, right? Whereas the following 7 bits, they are what convey the information, right? Which is why we have 7 over 8. There's one check bit that's used, and the remaining 7 digits are used to convey information. So there's 7 bits of information over 8 bits of total length. Okay. So it just kind of measures, yeah, like I said, like kind of like efficiency, right? Like how much of the code word is used to convey information, and how much of it is kind of, in a sense, redundant. It's useful in checking for errors, but it's redundant in conveying information. Okay. So that's kind of using this interpretation or this way of calculating it, right? Let's have a look at another example that will make use of this this way. Okay. So another example to consider is the set of code words here. They're all of fixed length. They're all of fixed length 4. Right, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, and so on. Okay. Now, again, the denominator is the same, right? It's just the length of the code. In this case, our denominator will just be 4. Okay. Our numerator on the other hand, will be log base 2 of 5. Right? Why is that? Well, our radix is 2, right? We're only using zeros and ones, so it's clearly like a binary code. And furthermore, the cardinality of our code set is 5, right? Because there's 1, 2, 3, 4, 5 codes in this code set. Okay? Let's get some intuition as to why this is similar to this. Right? So our numerator should be the number of information digits. What this log does is essentially tells us, on average, in each code word, how much of it actually is needed to convey the information that we want. Right? So essentially, in this code set, we have 5 different code words. So in this code set, it wants to be capable of distinguishing between 5 different symbols. Right? For example, S1, S2, S3, S4, S5. You want a code set that has enough code words that can distinguish between 5 symbols. Okay? Well, since we're using our binary code, right? Since we're using a binary code, we would have that in each digit here, you can either choose between 0 or 1. Yeah? So essentially what you have here is 2 to the power of x equals to 5. Right? You want to ultimately have enough digits in your code word to convey enough information to distinguish between 5 different symbols, right? So each single digit can choose between 0 and 1, so it's 2 to the power of the number of bits you need equals to 5. And so on average, the number of bits you need to convey convey enough code words to distinguish between 5 code words is going to be log base 2 of 5. Okay? So that's kind of where this intuition comes from, right? So again, 2 to the power of x equals 5. You can kind of interpret it as how many binary digits do you need in each code word on average to give enough code words, to give enough information to convey and to distinguish between 5 different symbols. Okay? And to do that, you can just solve for this and get that x equals to the log base 2 5. Okay? All right. Let's move on to the next slide. So that was information rate. Here is where we get first introduced to our first code here that has some error detection and the different strategies that we can use on what we wish to detect and correct. Okay, so a binary repetition code is simply a code that repeats a particular symbol a fixed number of times. For example, there's a bunch of examples here, right? And sorry, these are not examples. These are strategies. So for example, I'll write an example up here. A 3 binary repetition code, so a 3 repetition code, would either have the code 000 or 111 if we're looking at a 3 repetition code in a binary system, right? For example, the 5 repetition code, so the 5 rep code would be 00000 or 11111. Okay, that's all this means, right? All it means is you just repeat a particular symbol. In this case, it's binary, so either 0 or 1. You repeat that symbol just that many times. Okay, that's all this means. Okay, but this is a great segue into talking about how we can apply different strategies to have different forms of detection and correction of errors for corrupted codes. Okay, so in this example, let's have a look at odd and even number of zeros and ones. Okay, so let's say we have in this case, it's a binary 5 repetition code here, right? It's of a fixed length of 5, and here we have a binary So in this binary 5 repetition code, we should, in our set of code words, only ever see 0, 0, 0, 0, 0, or 1, 1, 1, 1, 1. In our binary 6 repetition code, we should only ever see 0, 0, 0, 0, 0, 0, or 1, 1, 1, 1, 1, 1. So all of these code words here are examples of corrupted code words because they don't belong in the set of binary 5 repetition codes, and neither do they belong, and these ones here don't belong in the binary 6 repetition code. Okay, so what can we do about these corrupted code words? Suppose we take on our first strategy. So strategy 1. Okay, our first strategy is we are happy to detect or to correct up to 1 error. Okay, what does that mean? That means, for example, in our set of code words here that are of a odd fixed length of 5, right? We can see, I'll change color. We can see that there is an error here and an error here, and we're happy to correct it. Okay, that's all this is saying. For strategy 1, we're saying that if we can see a single error, then we're happy to correct that single error, right? So we see a single error, supposedly, in this, and so we're happy to change this into 0, 0, 0, 0, 0. Okay. Similarly, in this last code word here, again, we see a single error, right? We see that this 0, we believe it to have used to be a 1, and it got flipped to a 0. And so we see a single error here, and so we're happy to correct it to a 1. Okay? That's all this first strategy is saying, right? And note that these are strategies. They're not guaranteed to be correct, right? Because for example, in this case here, we don't for sure know that there was just a single error, right? It may have been that it used to be 0, 0, 0, 0, and that it got corrupted into 0, 1, 1, 1, 1, right? It got corrupted 4 times here, right? We don't know whether we are correct or not, but we're saying we're happy to adopt the strategy, right? We're happy to say, if we see a single error, then we will correct that single error. Okay? And similarly for the binary 6 repetition code case, in this first code here, we see that, we see a single error, right? We see that this 1 does not belong, right? It is 5 zeros in a single 1. So we detect that this, or we suppose, we believe that there's a single error here, and so we change this 1 to a 0 to correct it to 6 zeros in a row. Similarly for this last one here, we see 5 ones and only 1 0, so we assume to believe that this 0 should not be a 0 and instead should be a 1. Okay, and that's all, right? So in strategy 1, we're just looking at the code, like the corrupted code words. If we supposedly see one error, then we correct it. Okay, we might not be correct, but that's our strategy. Okay, all right. Let's look at strategy 2. In strategy 2, we are happy to correct up to 2 errors. Okay. So in this case, we see 0, 0, 0, 1. Okay, we see 4 zeros and 1 odd one out, and so we're supposed to believe, or we assumingly believe that, okay, this 1 is not meant to be a 1; it's meant to be a 0. So we're happy to correct this, the same way that we were happy to correct that in our first strategy. Same thing here, we're happy to correct this to a 1. But on top of that, we're now also happy to correct these into zeros. And we're happy to correct these into 1s, right? Because we see 0, 0, 0, 1, 1, this corrupted code word, we can assume to believe that those last 2 1s there are errors. And so we see 2 errors, and so we're happy to correct 2 errors. Similarly, in the 0, 0, 1, 1, 1 case, we see that the 2 zeros at the front are possibly the errors, so we see 2 errors, and so we're happy to correct those 2 errors. Okay. Same thing with the even case here, on the 6 repetition code. Again, we're happy to change this to 0. We're happy to change these to 0, 0. We're happy to change this to 1, 1. We're happy to change this to a 1. Okay. All right. And lastly, I wanted to make an extra note here, right? In this even case here, this here kind of causes a problem for us, right? Because you could say, okay, we adopt strategy 3, which says we are happy to correct up to 3 errors. Okay, so this one must be a happy to correct up to 1, correct up to 2, correct up to 3. Okay, but the issue here is, even if we are happy to correct up to 3 errors, we don't know what to correct this to, right? We don't know what to correct this to, right? So obviously we detect that there's an error here, right? Because it's not all zeros and it's not all ones. But we don't know what to correct it to. We're happy to correct it, but we still don't know what to correct it to, right? There's an equal number of zeros, there's an equal number of ones. Should we correct it to all zeros or should we correct it to all ones? We do not know, right? So that kind of outlines a potential issue with even codes, and that's even if we bump up our strategy to be willing and happy to correct a higher and higher number of errors, at some point at the midpoint of even numbers, we will be stuck because we don't know whether to correct it to like this symbol or that symbol. Okay, and hopefully throughout these 3 examples, you kind of see a little bit of a pattern that we'll come back to later in T error correction. And essentially that is that with an odd binary repetition code, you have that, for example, you can represent this fixed length to be 2t plus 1, right? In this case, it's 2 times 2 plus 1, and the even binary repetition code is 2t plus 2, or in other words, 2 times 2 plus 2. Okay, right? There's 5. There's a fixed length of 5 here, and there's a fixed length of 6 here. And this t actually represents what we're capable, like what's the strategy with the highest number of errors we're willing to correct up to is. Okay, so for example, with this 5 binary repetition code, we at most can correct up to 2 errors, right? You can't say we correct up to 3 errors, like we can, but like that would be the same as saying we're willing to correct up to 2, right? Because if we correct up to 3, that would be the same as saying we're happy to correct up to 2, right? So in a sense, what we have here is that for 2t plus 1 fixed length codes, we can use a strategy that corrects up to t errors, right? You can't exceed that because again, once you exceed that, it's the same as doing like it's symmetric across both sides, right? And for even codes, so t plus 2 codes, similarly, we can use a strategy. Our maximized strategy can only correct up to, only correct up to t. Okay. The same thing here, right? With our 6 binary repetition code represented as 2 times 2 plus 2, we can at most develop a strategy that corrects up to 2 errors, right? We can't go to 3 for the very reason that we said here, right? And so this is a pattern that can be generalized, right? For any binary repetition code of any size, we write the number as 2t plus 1 or 2t plus 2 if it's even, and then the number, or like the strategy with the highest number of errors you can correct up to, will always just be the number t. Okay. All right, let's have a look at binary Hamming codes now. A binary Hamming code, with this, like with the parameters n and k, is a code of fixed length n with k number of information bits, such that it is single error correcting and has a parity check matrix H of size n minus k by n. Okay. I'll show an example first. So an example, a very common example is the Hamming 7-4 code, where we have the following parity check matrix. Okay. So essentially, I'll give a bit more of an explanation. So you just saw here that a matrix H can be like this, right? So we have some matrix H. We have some matrix H. Okay. The code set, the set of code words, is generated from all of the code words. Let's put them in vector notation X. For example, X1, X2, X3, blah, 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 all the way to Xn, such that H, so matrix multiplied by a vector, ends up being the 0 vector. Okay? And this thing here is also commonly called the syndrome. Okay? So the code set will just be all of the code words, such that when you take the syndrome with respect to our parity check matrix H, you get the 0 vector back, right? This is just by definition, okay? Yeah. And another way to think about this would be, so, okay, and the reason why it's called a parity check matrix would be because suppose you are sending a message X, it gets corrupted to the message Y, okay? Again, a binary Hamming code is only single error correcting, so suppose that there's only a single error here. We can express this Y as being equal to X plus some basis vector, right? Because, for example, our X code, let's say it's a code of 10110, right? It's a code 1010, and let's say Y ends up being the error, or like the corrupted code 00110, then we could have expressed Y as being equal to X plus 10000, right? Because in modulo 2, 1 plus 1 gives us 2, 2 more 2 is 0. That's why we got the 0 up here. Yeah. So we can always express our received message as being the sent message plus some error term here, which is simply just going to be the basis vector, like one basis vector at the position I. In this case, this would be the basis vector at position 1. Okay. And then we take our parity check matrix and multiply it by this equation on both sides, and this will give us that, right? And H of X, well, since X is a genuine code word, it will satisfy the condition that the syndrome equals to 0. So this will be 0, the 0 vector, plus this, right? And so this will help us detect errors, right? And will furthermore help us correct errors, as you will see a little later when I go through how we can use binary Hamming codes to correct errors. But here, this is enough to outline that by taking this parity check matrix, we can multiply on both sides of this equation, right? Calculate the syndrome of Y. So in this case, this is the syndrome of Y. And if it returns a non-zero vector, then we know that an error must have occurred somewhere. Okay, this is a very brief overview of how the binary Hamming code helps us detect errors, and we will soon also see how it helps us correct errors. Okay. So yeah, this is a common example. A question that you might wonder is, why in particular 7-4? Why not 6-4? Right? So why do we need to have why is this Hamming code in particular of fixed length 7 with 4 information bits, and not, for example, 6 fixed length and 4 information bits, right? Well, the answer is that you could have a 6-4 code, just that 7-4 maximizes the efficiency. All right, so Hamming codes are codes that kind of, I guess in a sense, maximizes the efficiency of check bits. Right? So if we think about it at the moment, we have a fixed length of 7, and we have 4 information bits. So if we have 1, 2, 3, 4, 5, 6, 7 bits in the code word, 4 of them are information bits. That means the remaining 3 of them act as check bits. Okay? And it just turns out to be a fact that if you were to be given 3 check bits, the maximum length of the code that you could have and still retain the single error correcting property is that it can be 7. Right? So I'll answer here. So 6, 4. Oops. 6, 4 is not impossible. It is just that. It's just that when having 3 check bits, the 7, 4 code makes use of these 3 check bits to the fullest. Yeah? So it's not saying that 6 4 is not possible. It is. It's just that if we would allow up to 3 check bits, then having a fixed length code of 7 would maximize the usage of these 3 check bits. Right? And if you're wondering why this is the case, there's kind of this expression here where you have 2 check bits to the power of the number of check bits minus 1 has to be greater or equal to the power of n. Oh, sorry, greater than n. Okay. You can see a more detailed explanation in your notes, but essentially it's just saying you need to have enough combination of check bits to cover all the possibilities of having a single error, right? So this left-hand side represents the total number of combinations of check bits that you could have that would help you check if there's an error. And n, this represents the length of your code. So if we're having a code that has a property of being single error correcting, that means if your code word is corrupted in the first position, it needs to be able to correct it. If it's corrupted in the second position, it needs to be able to be correct. It needs to be able to correct it. If there's a corruption in the third position, it needs to be able to correct it, and so on. And so, how many of those issues are there where there could be a single error? Well, there'll be n of them, right? Because in a fixed length n code word, the error could be in any one of the n positions, and so you kind of get this inequality where you need enough rearrangements of check bits to cover all the possibilities of there being a single error somewhere in your n length code word. And then once you rearrange this, you will see that you get n equals to 7 when the number of check bits is equal to 3, right? So you'll see 3 cubed minus 1 greater equal to n means that we have 7 greater equal to n, and so the maximal length we can choose n to be is 7 to optimize the usage of our 3 check bits. Okay. Again, there's a more detailed explanation in your lecture notes, but that's just a very brief intuition as to why. Okay. Next, we have some properties of Hamming codes. Like some water first. And that is that the dependent columns of H are the positions of the information bits, and the independent columns of H are the positions of the check bits. What is intuition behind this? Okay. Well, let's look at our H matrix here. Right? Firstly, we know that by definition, there should be 4 information bits. Right? And firstly, under this property, that's exactly how many information columns, I guess you could say, we have, right? We have 1, 2, 3, 4 dependent columns, which we are claiming here to be the positions of the information bits, and that makes sense because by definition we wanted this code to have 4 information bits in the code words. Correct? Okay, but now perhaps the bigger question is, why does it have to be the dependent columns that are info bits and independent columns that are check bits? Well, if you think about it, it's kind of this way by design, right? In a sense, we want to be able to convey whatever information we want, right? So I guess firstly, this is by design, okay, right? We want to be able to construct any message using our information bits that we want, right? And so for any given information bits, we want there to always be solutions, a unique solution for the check bits that then form our message. For example, in our 7-4 timing code here, we have 1, 2, 3, 4, 5, 6, 7. We have an info bit in position 3, info bit in position 5, 6, and 7, right? For whatever rearrangement or combination of values we choose to be in this 3rd, 5th, 6th, and 7th position, we want it so that there will always be a unique solution. So we want a unique solution for these check bits, right? We always want, no matter what information bits we choose here, and here, no matter what information bits we choose, we always want to be able to solve uniquely for these other 3 check bits. And the only way to guarantee that we will have unique check bits every time would be that they are the independent columns of our parametric matrix H, right? Because so that whenever we solve this, for example, times by, I guess, maybe I'll do it like this. So I'll call this check bit 1, check bit 2, information bit 1, check bit 3, information bit 2, information bit 3, information bit 4. Right? When you take the matrix multiplied by this vector, right, equals the 0 vector, right? You want to solve this equal to 0 vector. You want there to be unique solutions for your check bits, and so you want your check bits to be denoted by these independent positions, right? In these independent columns. Okay? Yeah? Because when you do your augmented matrix and solve blah blah blah, you will only ever get the unique solutions as part of your independent columns positions. Yeah? Okay? I hope that kind of makes a bit of sense, right? So it's by design, for any information bits, we want to always be able to solve this augmented matrix such that we get unique solutions for our check bits, and therefore our check bits must be in the positions of the independent columns, right? That's the only way we will get guaranteed unique solutions every time. Yeah? Okay. So how do we use Hamming codes to correct errors? We kind of talked about this briefly earlier, but essentially, if we have x that gets corrupted into a y, which can be rewritten as x plus 1 basis vector in the position position I, we can then calculate the syndrome for y, which would be h times x plus ei, which becomes 0 vector plus hei. And how does this tell us where the error is? Well, note that h, which is a matrix, times by a basis vector in position I, will just return us one of the columns of H, right? You go back to the matrix H, imagine taking this matrix H and multiplying it by a basis vector, right? Let's imagine we multiply it by, 0. It's kind of hard, it's there's not much space here, but suppose we multiply it by, say we multiply it by 0, 1, 0, 0, 0, 0, 0 transposed, okay, right? Then all this would do is that it would extract the second column out of our matrix H, right? And so in the syndrome calculation, we would get 0, 1, 0 as our answer. And we look back at our matrix H and be like, oh, 0, 1, 0 is the second column in our matrix. And therefore, this I here must have actually been 2, right? And then that will tell us that there's an error in the second position. And then since we're working in a binary setting, we know that there's an error in the second position. It is either a 0 or 1 right now. To correct it, just flip it to be the other one. If it's 0, flip it to be a 1. If it's 1, flip it to be a 0. And that's it. Okay? So here's an example. Suppose we're using the binary Hamming 7.4 code and we receive the following message. Correct the encoder message and determine what the information was. So let me copy down the H matrix first. So it's okay, it should be this. So H 1, 0, 0. It should be 0, 1, 0, 1, 1, 0, and then what? 0, 0, 1, 1, 0, 1, so 0, 0, 1, 1, 0, 1. It should end up 5 to get the 6. You go this, then 7. Okay. Yep, that's correct. Okay. So this is our H matrix, and we want to correct the encoder message here. Okay. What do we do? Well, we know that Y here is 1, 0, 1, 1, 1, 0, 1, right? And so we calculate the syndrome of Y. The same as H times Y, which ends up being the same as 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1, times by 1, 0, 1, 1, 1, 0, 1. Okay? And this ends up giving us let's have a look at this. So we get 1, 0, 1. This ends up giving us 0, 0, 1, right? Just based off my previous calculations, you can check this yourself, right? Just check this yourself, right? But you end up getting 0, 0, 1, okay? And now we look back at our H matrix and see, oh, 0, 0, 1 is in the 4th position, right? It's the 4th column. And so we know that in our encoded message, the error must have existed right there, okay? And so we can correct Y to 1, 0, 1, 0, 1, 0, 1. We flip the 1 to a 0, right? And now if we actually calculate this as well, so this is now x, right? If you can calculate x, like hx, this equals to 0, right? Go to check this, right? So note that once we have corrected it, if we now calculate the syndrome for x, it should return the 0 vector, right? Now we're not quite done yet. We now have to determine what the information was. Well, if this was our encoded message, recall that the information bits are in the positions where we have dependent columns, right? So that would be positions 3, 5, 6, and 7. So if you look at this one, it would be 3, 5, 6, 7. Yeah? And so the information that was intended to be sent is 1, 1, 0, 1. Okay? That's example 2. Example 3. Check whether a random string of 15 ones and zeros have a 1/16th chance of being a code word in the binary Hamming 1511 code. Okay. So, note that in a binary Hamming code, here we have a fixed length of 15. So the code length is 15 symbols, 15 bits. and it's 11 information bits, which means that there are 4 check bits, right? So there's 15 minus 11 equals to 4 check bits. Okay? And remember, in the intuition that we explained here, the whole point was, by design, we can have any information bits we want, and then by doing the by calculating the syndrome, we can reverse engineer it such that we can uniquely choose values for the check bits to ensure that the syndrome is a 0 vector, right? So going back to here, in our string of 15 ones and zeros, for 11 of those positions, we don't care what they are, right? For those 11 information bit positions, we don't care what they are. They can't be anything, right? The only positions that we care about are going to be those 4 check bit positions, right? We need those 4 check bit positions to be the unique solution to that augmented matrix when we solve it, yeah? So the positions of the 11 info bits, we do not care. We do not care about, right? We only care about the values of the 4 check bits. Okay? We need these 4 check bits to exactly match up to what the unique solution of that augmented matrix would have been given those 11 information bits, right? And so, what's the probability that these 4 check bits exactly match up with what they are meant to be when we solve it uniquely? Well, it would just be the first check bit getting it correct. We have a half chance, right? It can either be 0 or 1. The next check bit getting correct would again have half chance, right? Because it can either be 0 or 1, and so on. And so this is indeed equal to 116. Okay, so the answer is yes. Yes, it's true. Yes. Okay, I'll say yes. Yeah. So yes, it's true, right? We have a random string of 15s, 1s, and 0s. There's going to be a 1 in 16 chance that ends up being a valid code word in the binary Hamming 1511 code. Okay. A remark here is the Hamming 1511 code is as follows. I just wanted to point out. Actually, no, yeah. This is an extra note here. This is the 1511 Hamming code. Okay. Okay. A final remark on binary Hamming codes is a bit of a reflection on the information rate that we looked at earlier, right? As you can see, as you increase the number of information bits, the number of check bits you have also increases, but it increases much slower than the amount of information that you can convey, right? Which actually makes it pretty good, right? Because that means as you increase the number of information you want to send, the efficiency of a code goes up, right? Clearly, as you can see, as you go down, right, R increases. Yeah. Okay. So that's really good. But the issue with binary Hamming codes is you will ever only be able to correct up to 1 error, right? By design, this code can only correct up to a single error, right? So it's great that as we increase the number of information that we want to send, the efficiency goes up. But in terms of error detection and correction, you will always only be able to correct up to 1 error, which is no good. Okay. So that's my final remark on Hamming codes. Let's move on to having a look at Hamming distance and weights. For the next few definitions, suppose that the code words x and y are 2 n-bit code words, so the fixed length n. And let C be the set of code words. Okay. Yep, I just see the chat here. Zhang, yes, this session will be recorded. You'll be able to view this recording from the same link afterwards. Okay. All right, so Hamming distance. is defined by, or I guess let's say denoted by D, and then the parameters x and y, and it's equal to the number of bits in x and y that differ. So for example, if x is equal to the code 0, 1, 1, 1, 0, and 1, and y is equal to 0, 0, 0, 0, then the distance between x and y is 3. Okay, so the distance here is 3 because they differ in 3 positions. And the minimum distance of C is just amongst all pairs of code words in the code set C, what distance between any of these pairs are the smallest. Right? So for example, if you have 1, 0, and 1, 0, 0, 0, and you have the extra code, let's say 0, 0, 0, 1, right? Then the minimum distance of C would be 1, right? Because the minimum distance would arise out of this and this having a distance of 1. Okay, that's what that means. So then, yeah, it literally just means, as I'll call this Z, right? Between x, y, and z, right? Change pen color. Between x, y, and z, which pair has the smallest distance between them, and what is that distance? That's all this means. Okay. Having weight, very similar. It's defined, or it's denoted by W of the parameter, in this case the vector, or like the code word x. And it's just simply the number of ones in x. And so for example, if you have a look at 1, 0, 1, 1 again, the weight of this is just 3, right? Because it's 3 ones. Same thing, same concept of minimum weight, just out of all of the code words in the set C, which one has the least number of ones in it, basically. Yeah. Okay. This allows us to introduce the idea of a minimum distance decoding. Suppose we denote D as the minimum distance in the set of code word C. So we're basically just abbreviating this to this. Okay. We will then develop an error correction strategy called a minimum distance decoding, and I will illustrate such strategy right now. Okay. Suppose we have the code words in C are of an even fixed length. So case 1, even fixed length. Okay, so every code word in here has a fixed length being an even number. Okay, now what you essentially have is you have a bunch of code words in here, right? Let's suppose you send one of the code words and it gets corrupted. Okay, now the worst case scenario would be if this corrupted code words, if this particular corrupted code word lands within the vicinity of 2 genuine code words, 2 valid code words that have a minimum distance apart. Okay, I'll draw that in first. So suppose you have one code word here and other code word here, and they are the minimum distance apart, right? And the code word that, or the message that we receive, ends up landing here. Okay, right? Why is this the worst case scenario, right? For example, if we look at 2 code words that are further apart, let's say we look at this, and then look at this, and the code word we, or the message that we receive lands here, right? This is a less worse scenario, right? This is a better scenario because we would have even more conviction that our received message actually was actually the same as this code word here, right? And so if we have a bigger distance between our 2 code words and we land within that vicinity, right, then we would have a even greater conviction that it belongs to any particular one of those 2 valid code words, right? And the worst case scenario would be when we land within the vicinity of 2 code words with minimum distance, right? Because that would minimize our conviction, right? So the strategy is basically you have 2 code words here, minimum distance apart. If it lands closer to this one, we choose this one. if it lands here, for example, and it lands closer to this one, then we choose this one. Okay, that's all the strategy is, right? It's very similar to our binary repetition example, right? When we look at these strategies, yeah, it's just seeing which one is closer to, basically, right? In strategy 1, we said we're happy to correct up to 1 error. So if it's only 1 digit off, a valid code word, we will correct it to that valid code word. Yeah, same thing here. In a more general sense, right? If we're closer to some particular code word, then we will assume that the intended message was to be that valid code word. Okay. All right. So if you think about it, let me draw this up a bit properly again. If you have an even fixed length, right? An even fixed length, or even fixed. Actually, no, it's the wrong thing here. An even minimum distance. D. Okay. Then between these two code words in the worst case scenario, they will have, let's say, 1, 2, 3, 4. Okay. They are 4 units apart, right? Okay, so they're 1, 2, 3, 4 units apart. Okay. Then what would I be happy to correct up to, right? So the code word that we receive, that the message that we receive that's corrupted, could land either here, here, or here, right? What would we be happy to correct up to? Well, we would be happy to correct if it landed here, because then we would assume that it was meant to be this. And we'd also be happy to correct it if it landed here, because we would be happy to assume that it is this code word, right? We would be not happy, I guess, or we wouldn't be happy to correct it if it landed here, right? Because just like in the binary repetition case, we're now unsure as to whether we should lean towards the left side or the right side. Okay. So very similar to the pattern that we discovered in the binary repetition code. If we have the minimum distance d and it's even, we can always rewrite d as being 2t plus 2. And then t is the max number of errors we are happy to correct up to. Okay? Okay? That's all that means. All right? I hope that makes sense, right? And I hope that it also makes sense that we're using the minimum distance as our criteria, because, well, that's a worst case scenario, right? Like if you had a, like this situation here where you had a further apart code words, then you would have even stronger conviction to lean to one side, right? But we want to have a strategy that covers all scenarios, and so in particular, we want a strategy that also covers the worst case scenario, right? That's the point of using the minimum distance as our criteria. Okay. Case 2. What if our d is odd, right? Very similar thing, right? Like let's suppose you have two code words here that are minimum distance apart, okay, and they're odd number of units apart. So let's say 1, 2, 3, 4, 5. Okay. Then in this case, we would be happy to correct the corrupted message if it landed here or here, right? Like we would happy to correct it to here. We'd be happy to correct this to here. Simultaneously, if it landed on the other side, let's say here or here, we would be happy to correct it to here, or we would be happy to correct it to here. Okay? And so again, for any odd d, we can always re-express d as 2t plus 1. And then same thing as the binary repetition code, we would always be happy to correct up to t errors. Okay? And this just summarizes what I said here, right? If it's odd, we can always correct the t errors if we re-express t as 2t plus 1, and similarly for the even case. Okay. We have another theorem here called spear packing. A T error correcting radix R code C of length n has a minimum distance d either being odd or even, and then the number of code words must satisfy this inequality. If you read from left to right, it's saying the number of code words times by that weird sum there must be less than or equal to r to the power of n. Okay, and we can interpret this right hand side, r to the power of n, as being total number of possible code words. Right? So if you have radix r and you have a length of n, then in each position across this n length code word, each one of them can be any one of the 0, 1, 2, 3, 4, all the way to r minus 1, right? So you have r to the power of n, total number of possible code words. Okay. This we can also interpret as just being the number of code words. And this is what we have to figure out. Like, what does this mean, right? So what's the intuition behind this? Actually quite an interesting reasoning. It ends up actually having to do with tessellating shapes, basically, right? So suppose you have some set here, which is the realm of all possible code words. So this here is your Rn, right? You have r to the power of n number of objects in here, okay? And let's suppose that in this r to the power of n, only some of these are actual valid code words in our code set, right? Let's suppose that there's one valid code word here, let's call it C1, one valid code word here, call it C2, one valid code word, call it C3, and so on, right? They're all scattered across this realm, right? And in C1, right, in the vicinity of C1, if we're using the minimum distance decoding strategy, in the vicinity of C1, what are we willing to correct up to, right? Well, if the minimum distance is d, under the minimum distance decoding strategy, we're willing to correct up to exactly t errors, right? We're willing to correct anywhere between 0 and t errors. If there's 0 errors, then it will be exactly C1. If there's one error, then perhaps we're willing to correct up to this vicinity around C1. If there's 2 errors, then we're willing to correct up to this vicinity around C1, and so on. And ultimately, we're happy to correct up to a vicinity of t errors around C1, right? Okay, and that's kind of logic so far. And now you might ask, why n choose 1? Why n choose I? Well, the reason is, in a nth length code word, if you have a code word that has 2 errors, for example, two errors, for example, then there's going to be nc2 number of positions where those 2 errors could be, right? That's why you have n choose 1. They kind of represent the possible positions that those number of errors could be in your n length code word. And your r minus 1 to the power of I is just what is it corrupted to, right? So for example, if you have an error in position 3 of your n length code word, right? Since it's radix r, that third position bit can be corrupted into any of the r minus 1 other digits in your radix, right? So for example, if currently in position 3, your valid code word would have the bit 1, it can get corrupted. That single 1 can be corrupted to either 0, 2, 3, 4, 5, all the way to r minus 1. So every number from 0 to r minus 1 except for 1 itself. That's why there is r minus 1 possibilities of what that single bit can be corrupted to, raised to the power of I, because I number of bits are corrupted. Okay? And now kind of repeat this logic for all the other code words, right? That's why it's multiplied by the cardinality of C, right? If you think about it, C3 will also have its own circle around it. C2 will also have its own circle around it, and so on. And so for every single code word in here, they will have a circle around it. Now note that these circles will never overlap. They will never overlap because we're using the minimum distance decoding, right? They're done so such that, for example, if I go back and draw circles here, by design, this strategy makes it so that these two circles will never overlap, right? For example, here as well. Like this. Right? These circles will never overlap, right? Because once you reach the midpoint for an even minimum distance, like you're not gonna do any correcting. And similarly here, well, clearly there's also some gap between the circle, right? So ultimately, you have a bunch of circles that are not overlapping, and circles are non-tessellating, and so the area of these circles can never fill up the entire realm of all possible number of code words. And so that's why you have this inequality of being less than or equal to r to the power of n. An extra thing to mention here is that, extra fact is that a perfect code is one where equality holds, right? So a perfect code would be a situation where the circles perfectly fit the entire R, right? But they're very rare. Okay. Binary linear codes. It is essentially a generalization of Hamming codes shown previously, right? So instead of having these specific looking matrices, like for example the 1511 matrix or the 7-4 matrix, right? Instead of having these specific matrices, you just in general have a parity check matrix, okay? But they work very similarly, right? Because then your set of code words comes from all of the x's, such that when you do your matrix multiplied by your vector, you get the 0 vector, okay? All right. And again, a binary linear code now, in general, may not necessarily require you to only be able to correct up to one error. Right? We can develop binary linear codes that are able to correct up to 2 or 3 or 4 or 5 errors and so on. Right? So in that, like in that sense, something else has changed, right? So x gets corrupted to y, but now our y doesn't just have to be that. So it doesn't just have to have an error in the ith position. It can also have an error in the jth position, an error in the kth position, an error in the lth position, and so on. It can have as many errors as this parity check matrix permits it to have. Okay. And so what this does is now it makes using the code a little harder, because now if you think about calculating the syndrome of y, h times x will give us the 0 vector, but then now you will have a linear combination of the columns of h, right? You have a bunch of different basis vectors times by h, so you can potentially have a linear combination or a summation of these different columns of h. Okay. A theorem is that we have minimum distance for linear codes. The minimum distance d of a linear code with the matrix h is going to be the smallest integer r for which there are r linearly dependent columns of h. We will see an example of that soon. Right, so example 4. We received the message 10001, correct encoded message, and the term what information was. I'm going quite a bit over time, so I'll just very briefly mention it, and then you can check through the working yourself. But essentially, you're going to take this matrix H, multiplied by your received message, so like this, right? And you should realize that this ends up being equal to 2001, which under mod 2 is exactly equal to 0001. Right? Okay. And now note that 0001 or 2001, both of these vectors, no matter which one you decide to use, is not any particular column of your matrix H. Right? And this is exactly the whole point of what I said earlier, right? Like right here, you may no longer get a syndrome that is just exactly equal to a single column of your matrix H. Yeah? In this case, we don't. But what do we realize? We realize that this vector, 2001 or 0001, is just the summation of this column and this column. Okay? And so we know that this is equal to 1000 plus 1001. And so there must be an error in the first and fifth position. And so our message should be corrected to 0, 0, 0, 0, 0. Right? This one gets flipped to 0, and this one gets flipped to a 0. And so what was the information? Well, again, same property from Hamming code also extends over to here. The dependent columns are the information bits, and the independent columns are the check bits. In this case, the only dependent column is the last one, right? The rest of these all have leading terms in each column. And so only the last bit is an information bit, and so the info is just a 0, right? It's just this last 0 here. Okay. Example 5. A binary linear code C has this parity check matrix. Find the probability okay, so I guess firstly the code word X is transmitted through a noisy channel, in which case each bit Xi can be corrupted with an equal and independent probability P. Find the probability that all errors are corrected correctly when using the minimum distance decoding strategy. Find the probability of detecting at least one error when using the pure error detecting strategy. Alright. So in question A, we're looking at if we're using the minimum distance decoding strategy, what is the probability that we correct the errors correctly? This will make use of our theorem earlier, theorem 3 here. Okay? We don't even know what the minimum distance is, but we can figure it out quite easily using this theorem. By looking at our matrix, right? Are there any two columns that are linearly dependent? No, right? Because no pair of columns here are scalar multiples of each other. Are there any triples of columns that are linearly dependent? Well, by inspection, also no, right? Because you can't have, for example, column 1 plus column 2 equals column 3, or column 2 plus column 3 equals column 4, right? That just doesn't happen. Are there any set of 4 columns that are linearly dependent? Well, yes, right? Because these first 3 columns add up together will give you exactly the last column here. Okay? And so we notice that the smallest set of columns that are linearly dependent is 4, right? And 4 can be re-expressed as 2 times 1 plus 2. And so we notice that by the minimum distance decoding strategy, it will be happy to correct up to 1 error, right? Because t is 1, okay? All right, so in the minimum decoding strategy, we will correct up to 1 error. And so what's the chance that all corrected errors were corrected correctly? Well, that would be the case when there is actually indeed just 1 error, right? So our strategy will always correct 1 error if it sees an error and it will correct it. So the probability that it being corrected correctly is that in the transmission, there is actually only just 1 error, right? What's the probability? Well, you have 4 bits. So what's the probability of one of those bits being corrupted? Well, that would just be equal to 4 times p and 1 minus p cubed, right? So the 3 bits are not corrupted. 1 bit is corrupted, and that 1 bit that's corrupted can be in position 1, 2, 3, or 4. So times by 4. Okay, and for part B, find the probability of detecting at least one error when using the pure error detecting strategy. So this will essentially be if you don't even want to correct anything, you just want to detect errors. Well, you would only detect errors if there is 1, 2, or 3 errors, but not 4 errors. Why is that? Well, notice that this matrix here is actually the parity check matrix for a binary repetition code. How do we know that? Well, for example, in this last column here, the only dependent column in our matrix, this is our information bit. Correct? And suppose we set this information bit to be equal to 0, right? We set it to be equal to 0. Well then, if you solve your augmented matrix, you will notice that your check bits by backsub must also all be 0. Right? So for example, you will have the augmented matrix. Right? Okay, all the blank spaces are just zeros. And so this will imply that you will have x, for example, x3 here is equal to negative x4, right? x3, x4. You also get x2 is equal to negative x4. x1 is equal to negative x4, right? So if we set x4 to be 0, well then under modulo 2, x4 will be 0, but so will x1, x2, x3. Similarly, if we set x4 to be equal to 1, negative 1 modulo 2 is the same as 1. So if x4 is 1, then x1 will also be 1, x2 will also be 1, x3 will also be 1. And so in this code set, you will just have the code word 0, 0, 0, 0, and 1, 1, 1, 1. Which is exactly the binary repetition code, right? Recall what we did when we looked at the binary repetition code. We saw that, for example, if you're willing to correct up to whatever number of errors, the only way no errors are detected would be if there are actually no errors, or if there is errors everywhere, right? Because if there's errors everywhere, the binary none of our strategies would detect that none of our strategies would detect that there was an error in the first place, right? Because they're all ones, there's no odd one out. We would just assume that, okay, well, it's all ones, so it must just be all ones. Yeah? And so the probability of undetected error would be, the probability of detecting at least an error would be 1 minus the probability of no errors and minus the probability of everything is an error, right? Which should be exactly equal to 1 minus no errors is this, and 4 errors is this. Okay. Error mark here. So yeah, it was great that in part B we saw that it was a binary repetition code, and so we could just go straight into using what we learned about binary repetition code previously. But what if we did not even consider to check whether this was a binary repetition code? What could we do then? I'll probably leave this as an exercise for you to think about yourselves, because again, running out of time. But essentially, you will just have to look at the linear combination of columns. Okay. Yeah, that's the main hint I would give you. Right. Look at the linear combination of columns, and essentially you want to see what your y can be corrupted into, right? Like what extra stuff you add up here, such that h of y is 0. Okay, right. So you want to find out where can the errors occur, such that h of y is still going to stay at 0, and then look at the probability of those errors occurring. Okay. Generated matrices. This is an alternative way of thinking about how a set of code words can be created, right? So previously we looked at generating code words by saying that it would be any vector when multiplied onto your matrix H gives you the 0 vector, right? So basically every code word is where the syndrome returns the 0 vector. This is another way of looking at it, Instead, we have a generator matrix where all the rows of the matrix is just a basis, like all the basis vectors for C. And then every single, I guess you could say, like multiple, right, or any like linear combination of G will return you all of the code words in C. Right? It's a bit abstract right now. It's just by definition, so don't worry too much if it doesn't fully make sense. But just by definition, if we have a matrix such that the linear combinations of all of the columns of this, if we have a matrix where the linear combination of these rows form all of the code words in C, then you have a generator matrix called G. Okay. Another thing to think about is, or to look at, is standard form matrices. The idea here is to provide a link between the previous definition and this generator matrix definition, right? Suppose we can write, and suppose we have H, a parametric matrix from the previous definition. Once we reduce H and change its columns around, permute the columns around, such that the first few columns is a identity matrix, we then have this form here, where we write H dash, like the transformed parametric matrix, as being a matrix where the first few columns are just all filled with, I guess, for example, something like this. And then B could be, I don't know, like that, right? So in this case, you can see in this first three columns, you have a identity matrix, and then in the remaining three, you have some other matrix B, okay? And any sort of check matrix in this form is called a standard form check matrix, okay? Now the link between H and G would be, if you can rewrite H in this form, then you can instantly get your G as being the two things swapped around. So B down the front, the identity matrix to the back, but also your B matrix is transposed and you chuck a negative in front. But for our intents and purposes, the negative sign disappears because we're usually working in mod 2, right? We're working in binary. Right? And so this negative is just, because negative 1 is just congruent to 1 in mod 2. So the negative can disappear. Okay? So an example here would be this question here. Suppose we are given that there is a binary linear code C with check matrix given there. Find the basis for C. There's two methods. One method I'll go through right now, and the other method you can try yourself. Right? I'll outline what this other method is first, to be honest, and then I'll go through the first method, which is much faster. The try yourself method is basically to use what you know about linear algebra, right? You know that the information bits are conveyed through the dependent columns, correct? And so if you want to find the basis for all of the code words in C, you essentially just need to find a basis for these dependent columns. Okay. Is that the right way to put it? You have these dependent columns, which are your information bits. Let me have a look. Okay, no, yeah. So you have these two dependent columns, and so you know that there'll be two vectors that form the basis for all of the code words, because again, only the information bits is what conveys the information. The check bits are just forced to be what they are, given your information, given your information bits. And so to find out what the basis of this is using linear algebra, we'll just solve this augmented matrix here, right? Letting x4, x5 to be free parameters. Okay. Yeah, that's it. So you can have a go at this yourself. The faster method here is to note that H is given to us in standard form, right? We have some identity matrix here, and then some other matrix B here, okay? And so we can rewrite, or like we can get our G straight away as being this matrix at the back transpose. So 1, 0 becomes 1, 0, 1, 1 becomes 1, 1, 0 becomes 0, 1, and then the identity at the back, okay? And recall, we had some property about the generator matrix being that the rows are the bases, and that's it. So the bases would simply just be the set of vectors 1, 1, 0, 1, 0, and 0, 1, 1, 0, 1. Okay? And that's it. Okay, lastly, extending binary linear codes to higher-radix. So an example would be extending a Hamming code to a ternary Hamming code. And as you can see, now the entries, right, the entries here no longer have to just be 0 and 1s, which makes it a little bit more complex, right? So entries can be 0, 1, blah, 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 all the way up to whatever the radii is minus 1, okay? And now another complication is that when calculating the syndrome, it becomes even more difficult to identify which linear combinations of columns form the syndrome, right? Because if we go back to what we had previously, over here we had x plus error in the first position plus error in the second position, and so on. But now, on top of that, you can also have scalar multiples of these errors, right? For example, you could have x plus 2 times EI plus 3 times EJ plus 1 times EK and so on, right? And so on top of just looking at linear combinations where the coefficients are 1, you now also need to look at linear combinations where the coefficients are not 1, okay? And that is another complication. And the last complication is when converting from your H to G using this theorem here, you no longer can simply just drop the negative, right? Because if you're under a different modulo, -1 won't necessarily be congruent to 1. For example, -1 in mod 3 would be congruent to 2, right? So this matrix on the left-hand side would now become a little bit more complicated, okay? And yeah, and that's it, right? I know the end is a little rushed, so I'm running out of time. I went quite a bit over time. Example 7, you can have a go at yourself. I will write up a proper answer and upload it onto the MathSoc site with all the annotated slides. We can read through the answers here. But I won't go through this one now. It's a bit of an extension question. I will now hand it over to Steve to go through topic 3. Just a heads up that this might run a little over time because I did take up quite a lot of time. But yeah, for those of you who can't stay for the entire time, that's fine. You can always watch the recording afterwards. But yeah, sorry about that. I'll now hand it over to Steve.
Hello, just testing the mic. Alright, okay, let's get started. Yeah, sorry for going over time. Jay went over 15 minutes over, but that's fine. We'll just continue on. Okay, so this chapter 3, in the previous section, we only really dealt with fixed length codes with a focus on detection and correction. In this chapter, it's going to be a different flavor. We're going to shift our attention to efficiency, in the sense that how can we decrease code word lengths compared to the fixed length codes while keeping the same information. For now, we assume that there are no errors because, well, intuitively, we only care about once we compress messages in some way, we can apply these same error correction detection techniques that we covered in the previous section. So to do this, we need to know a bit more about the source symbols, in particular their probabilities. And the basic idea is to encode the most frequent source symbols with shorter code words so that on average, the code word length of a message, the average length of an encoded message is reduced. So from here onwards, we're going to assume that S is a source. We're going to denote the source symbol from S1 to SQ. And we're going to say the code is C with code word C1 to CQ. P1 to PQ be the probabilities of each source symbol, and L1 to LQ be the lengths of each code word. So here's some basic definitions to start off. We say a code is uniquely decodable if there's only one way to decode any encoded message. So like if we have an encoded message, there's no ambiguities. There's only one way to decode it. And we say a code C is instantaneous if no code word is the prefix of another. And we call these I codes. So here's an example. It's called the standard comma code. And it kind of looks like this. We start off with 0 as the first code word, and then 1 0, and then 1 1 0, and then 1 1 1. So like if we have a length k standard comma code, then we'll end up with the last code word as k1s. And we can see that this is an I code because no code word is the prefix of another. So like for example, 0 is not a prefix of any of the other code words here. So yeah, so this is an I code, and it turns out that this is also uniquely decodable. Here's another example. We have another code, 0 1 1 0 0 1 1. This is not uniquely decodable, and this is because we can decode a message 0110 in more than one way. We can either do treat the first 0 as part of S1 and 110 as S2, or we can treat 011 as S3 and the 0 as a S1. So there's two ways of reading this. It's S1 S2 or S3 S1. And yeah, so that's how you, this is basically the general method in how you show whether a code is uniquely decodable or not. You just have to come up with an example message that you can decode in what you can interpret in two or more ways. We see that it's actually also not instantaneous, this code here, because C1 is a prefix of C3. And yeah, instantaneous means you can't have that kind of stuff happening. Here's another code, 0 0 1 and 0 1 1. Now this one is not instantaneous because C1 is a prefix of C2 and also C3, and C2 is also a prefix of C3. So yeah, because of that, it's not instantaneous, but it actually is uniquely decodable, it turns out. And we can kind of decode any message uniquely by reading from the right to left, kind of stopping when as soon as we see a code word, or as soon as we recognize a code word in here, and repeating for like the remaining left part of the message. So yeah, the key takeaway here is that all I codes, all instantaneous codes are uniquely decodable, but some uniquely decodable codes are not I codes. So it's like we have a subset relationship. The set of all I codes is a subset of the set of all UD codes. Okay, so if we do have an I code, how do we decode? Well, it's actually pretty easy. If we have an encoded message, we just start reading it from the left to right, and we kind of stop as soon as we recognize a code word. So we're kind of like doing a greedy strategy where we just interpret, or we kind of translate as soon as we recognize a code word into the corresponding source symbol, and we repeat this kind of strategy for the rest of the encoded message. So yeah, here's a question. Consider the source, 3 symbols, and they have the following code words 1 0 0 0 1. And yeah, we're told that this is an I code, and it is. None of the code words are prefixes of another. And the question is to decode this message here, 001 01 01 001. Okay. So wait 1 second. Yeah, okay. So yeah, here's the question. The way we do this, we start reading from the left to right this way. So we start reading from the 0, and we ask ourselves, is 0 a code word in here? Well, no, 0 doesn't appear here. So we keep going. We kind of extend our vision here. 0, 0, is that a code word? Yes, it's C2. So this part over here gets translated into S2. Now we repeat. So we read the 1 here. So 1, is that a code word? Well, yes, luckily it is. It's just this one over here. So we translate that into S1. Repeat again. Is 0 a code word? No. 0, 1 is a code word. So we translate into, well, it's the third code word, so the third source symbol. And then 0, 1 again. Oops. That turns into S3 again. And similarly, just keep going. We get S2, and finally we get S1. So the final, well, the original message was S2, S1, S3, S3, S2, S1. Yeah, it should be pretty straightforward. Okay, so yeah, that's how you get it. Now we have this theorem here called the Kraft-Macmillan theorem, and given some code word lengths, it tells us whether there is a uniquely decodable code or an I code based on like some quantity derived from these lengths. So I'll just show you the whole thing. Yeah, so what this theorem says is that these three statements are basically equivalent. So the main takeaway you need to get from this is that if you compute the sum over here, where R is like the radix and the L's are the lengths here, if you sum all of this up and you get less than or equal to 1, then that means there is a uniquely decodable code and an I code with these lengths, L1 to LQ. And if you can't satisfy the sum, so if the sum is greater than 1, then there is no, like there cannot be a radix R UD code nor an I code for those lengths. And this K here, this sum here is denoted K, called the Kraft-Macmillan coefficient. And this is just a measure of how, like kind of like a efficiency measure, loosely in terms of how compactly designed the code words are. You might have seen some other way of describing this, something like how much of the decision tree that is used based on the code word lengths here. But yeah, you can look back into the lectures if you want. Yeah, so for example, here there is no radix to UD code with code word lengths 1, 2, 3, 3, 3, because if you compute that sum over here, you're going to get 1 on 2 plus 1 on 2 squared plus 1 on 2 to the 3 plus 1 on 2 cubed plus 1 on 2 cubed, and you get 9 over 8, which is greater than 1. So there's no radix to UD code with these code word lengths. Okay. So here's a question. Is there a radix 3 I code with code word lengths 1, 1, 2, 3, 3, 3, 3? And if so, construct such a standard I code. I'll get to what a standard I code means. Okay, so here we go. It's the same question here. Alright, so there are two main ways of doing this. In the lectures, you would have seen Thomas have like this decision tree method where you kind of like branch off from the start, kind of add on new branches based on the new code words going from left to right here. If you want to see that method, just refer back to the lectures. I'm going to show you a second method, which might be more understandable for other people. So what we do is we look at the code word lengths from smallest to biggest, and for each code word length, we try to assign the smallest possible code word. So for example, to start this off, say this is for the first code word, we want it to be length 1, right? So since we have a radix 3, we want to build a radix 3 I code. This code word can only be 0, 1, or 2, and we choose the smallest one that we haven't used. So we just do it with 0. C2 Well, again, we need to be, we need to assign either 0, 1, or 2 for this because it's length 1. But we can't do 0, so we do the next smallest possible one. 1. It can't be 0 because C1 already took that code word. Okay, so C3, we want a length 2 code word this time. And so it's going to have to start with 0 to 2, and then the second digit is also going to be 0 to 2. But the thing is, we can't start it with a 0 or a 1 because that would kind of break the instantaneous property. Because if we do that, as soon as we do that, C1 or C2 is going to be a prefix of C3, and we don't want that. So we need to start this off with a 2. And to fill in the last digit, we don't really have any restrictions for that. So we just decide to put in like the smallest possible digit, so 0. Okay, so next we have C4. C4 is length 3. And again, for similar reasons as before, it can't start with a 0 and it can't start with a 1. So it's got to start with a 2 here. And next, we can't start, the second digit can't be a 0, right? Because if that was the case, then C3 would be a prefix of C4, and we don't want that. So we choose the smallest possible thing for the second digit, which should be 1. It won't be 2 because we can do better. We can do 2, 1, and still not break the instantaneous property. And for the third digit, we don't have any restrictions on this, so we just pick 0, the smallest one. All right, C5, it's length 3 again. The next possible one, it should be 2, 1, 1. Like that's the smallest one, bigger than the ones that we already used. And it still works because like none of the code words are prefixes in other still. Similarly, C6, we can do 2, 1, 2 without breaking the instantaneous property, and it's like the smallest one up from the previous code word. And C7, similarly, we can do 2, 2, 0, not something like 2, 1, 3 because we're in radix 3. 2, 2, 0 because it's the smallest one that comes after C6 and still doesn't break the instantaneous property. So yeah, there we have it. That's the this is actually how you build the standard I code, going from like always trying to pick the smallest code word for increasing length. Of course, without breaking the instantaneous property. Okay. So yeah, there's that. All right, so we were trying to talk about. I kind of mentioned efficiency, or like kind of compressing messages to the shorter lengths. And so yeah, that's the point. We were interested in making code words as short as possible, given the probabilities of the source symbols. And the more precise way of saying that is that we want to reduce the average code word length down to a minimum. So here's the definition. Consider a source. It has Q symbols, S1 to SQ. They have probabilities P1 to PQ. And they have also corresponding code words C1 to CQ of lengths L1 to LQ. So here are some definitions. So average length is just kind of like the weighted sum of the lengths based on the probabilities. It's kind of like the expected length in like statistical terms. And the variance, again, that's just straight up the statistics formula for variance. I don't think it's that widely used in this course though. Yeah, probably don't need to know much about the variance. The average length is the most important part. And we say that a uniquely decodable code is minimal with respect to the probabilities P1 to PQ if it has minimal average length. And this part here is important. We're only concerned about minimizing the average length for uniquely decodable codes, because if we don't have a uniquely decodable code, we can just like set every single code word to like 1, and that would, I guess, have the smallest average length, but will be a pretty useless code because there's so many ways of interpreting the same message. So yeah, here's an example. Let's say we have a source with symbol probabilities 2/3, 1/6, and 1/6, And suppose that the code words are 000, 1, and 10 respectively. So if that's the case, then the average length is going to be 2/3 times the length of its code word, which is 3, plus 1/6 times 1, because the second one is length 1, and similarly plus 1/6 times 2. That gives you 5 on 2 on average. The thing is, this code C, it's not minimal, because we can come up with another code that has a better average length. So consider another code with code words 0, 10, and 11. Then if you compute the average length, you get 4 on 3, which is less than 5 on 2. So clearly the first code is not going to be a minimal one because there's already something that's better. Just to be clear, this C dash here, that still might not be the minimal code word. It just shows that the first code is not minimal. And yeah, from here onward, let's just assume that we just rearrange the source symbols so that they have non-increasing probabilities. So the first one is going to have the biggest probability, and the last one is going to have the smallest probability. So here's a theorem. If a uniquely decodable code has a minimal average length L with respect to the probabilities of the source symbols, then we can have the following. So this kind of depends on whether we shuffle around the code words of equally likely symbols. We have L1 less than or equal to kind of like the lengths in increasing order, or non-decreasing, I guess. We have that the lengths of the two last code words are equal. And if C is instantaneous, as in C is an I code, then the last two code words, they only differ in the last place, the last digit. And if C is binary, it turns out that the Kraft-Macmillan coefficient is exactly equal to 1. And yeah, just to be clear, we're still assuming that P1, like the probabilities, are in decreasing order. So this is the first dot point is saying the smallest length is reserved for the most frequent source symbol. The rarest two code words, they're given the same length, and the rarest two code words, they also differ in the last place. So here's an example. If we have these binary code words 0, 10, and 11 corresponding to the probabilities half, a quarter, and a quarter, this is actually a minimal binary I code. We can't do better than this, and I'll let you figure it out, like why it's the case. And so because of that, according to this theorem, it satisfies all of these properties above. So we can check the first one. Well, are the code word lengths increasing? Well, yes, 1, 2, 2. Is the last two code word lengths equal? Well, yes, 2 and 2. Is C instantaneous? Yes. So, and do the last two code words differ only in the last place? Yep, only in the last place they differ. And is the Kraft-Macmillan coefficient equal to 1? Well, I believe it is. It should be half plus a quarter plus a quarter. So 1 on 2 plus 1 on 2 squared plus 1 on 2 squared, that gives you 1. So yeah, you can see that this theorem holds by example, I guess. So yeah, minimal codes are pretty cool, but how do we actually find one given the probabilities of a source, or of the source symbols? Well, Huffman's algorithm is what does this for us. So here's a bunch of dot points. You can read that later, but I believe actually doing this and showing you how to do it is more useful. So it'll be easier to see. This question, yeah. So the question is, use Huffman's algorithm to construct a instantaneous minimal code for the source of 4 symbols which have probabilities 0.4, 0.3, 0.2, and 0.1. So here's the question. So the way Huffman's algorithm starts is that we list these symbols in a column here with their probabilities. So like S1, S2, S3, S4. We want the highest probability symbol to be at the top of the column. And let's just draw, we just draw the probabilities of them. 0.4, 0.3, 0.2, 0.1. The next step is to sort of combine the bottom two symbols, so like the least frequent two symbols, and kind of add up their probabilities. So we have these two over here. We want to combine them. And if we add up the probabilities, we get 0.3. And we kind of treat that combined S3 and S4 as like a single symbol that describes both of them. So S3, S4 is going to be like a new symbol, like not an actual symbol, but like a new one that we created, which has probably 0.3. So we represent that as like just drawing branches into a 0.3 over here. And we kind of, for the nodes that, for the numbers that we haven't touched, we just like put them forward, just like as is. Now, the variant of Huffman's algorithm that we're going to use, we're going to always keep whatever new probability that we found at the topmost position of the column possible. That's like, it's kind of just saying if there are ties like this, like 0.3 and 0.3, we always want to make sure that the new symbol that we create goes on the top. So instead, we're going to actually have something like this. And yeah, so we kind of continue this. We again look at the bottom two symbols of this second column that we created. And that's going to be the two 0.3s here. If we combine them, we get 0.6. So it should end up at the top of the new column that we make. And the 0.4 should come back down. And finally, there's only two left. We just combine both of them into one. And finally, to just make it easier, we sort of label these branches on each column, just like going down with the digits in increasing order. So once we have this set up, the way you get the code words from this is that you kind of trace the path from each source symbol along the branches. Like it might not cross a branch that has a number, but that's fine. For the branches that you did cross a number, that's going to be like the code words. And you're going to have to read them in backwards order actually. So sorry about that. Yes. So this is going to be the one for S1. And on this way, you only encounter this one. So the code word for S1 is going to be just 1. Similarly, if we look at how S2 goes from the last node over here, it goes to 0, 1, and nothing. So C2 is going to be 0, 1. If we look at S3, it's going to go through like this. So it's going to be 0, 0, 0. So C3 is 0, 0, 0. And finally, S4, it's going to go like this. So 0, 0, 0, 1. So the fourth code word is going to be 0, 0, 1. And that's really it. That's just the Huffman code for these source symbols with their given probabilities. And it turns out this is a minimal one. So you can't really do better than this for these probabilities at least. Yeah, so that's where it is. Yeah, okay, so yeah, I just said that Huffman's algorithm gives you the minimum average code word length. To find this actual code word length, you can either just multiply the probabilities with the code word lengths that we found, or there's a theorem that makes it really, really easy for us. So Knuth's theorem says that the average code word length is of a Huffman code is the sum of the child node probabilities. And in other words, it's just the sum of the probabilities that we circled here along the way. So the probabilities of the newly created merged symbols. So by Knuth's theorem, the average length L for this code, it's going to be 0.3 plus 0.6 plus 1, which is 1.9. So it's just like these three over here. And if you want to check, you can kind of manually calculate the average lengths based on these code word lengths here, and you should see that they agree with this value. Yeah. Okay, so what we have seen so far is a Huffman code for radix R. I mean, radix 2, it was binary. The thing is, Huffman's algorithm can actually be used for any radix, but it's a slightly different slightly complicated algorithm. So if we notice, in the binary case, so radix 2, we merge the two bottom symbols on each column, and we can only and that was because we can only create two branches for like 0 and 1. If we have an arbitrary radix R, then we instead merge the R bottom, this R symbols at the bottom of each column at every step. The thing is, the complication with this is that if the radix that we're working with is greater than 2, we might eventually get a situation where some column at the in the later steps of the algorithm, we might not have enough of we might not have enough of the symbols to combine. So to avoid the situation, we need to kind of add dummy symbols with probability 0, so that the number of symbols is a multiple of r-1 plus 1. And that sounds really wacky, but the reasoning behind that is that, well, okay, it's not on the slides, but the reasoning behind that is that, for example, when we combine the two symbols in the binary case, we ended up with one symbol in the next column. So that was like a net decrease of 2 minus 1, so like one symbol at each column. If we merge R symbols at a time, then we're going to end up with, we're going to delete all of those R, merge all of them into one symbol in the next column. So that's like a net decrease of R minus 1 symbols as we move along the columns. So at every stage, every step of merging, we get rid of R minus 1 symbols. And since we only want to end up with one symbol at the very end, we're going to have 1 plus R minus 1 times the number of merging within as the number of symbols that we started with. So we're going to need this equation to hold here. So yeah, the number of symbols has to be multiple of R minus 1 plus 1. So here's an example. Use Huffman's algorithm to construct a radix 3 minimal I code for the source of 6 symbols there, with respective probabilities 0.3, 0.3, 0.1, 0.1, 0.1, 0.1. And so let me go over here. Okay, so as before, we just list down these symbols as before, just like in decreasing order of probability, and just write down the probabilities here. Oops. 1, 1, 1. And remember, we had to make sure that this equation holds. So the number of symbols that we have is going to have to be a multiple of R minus 1 plus 1. Since our R here is 3, we have radix 3, we need the number of source symbols to be a multiple of 2 plus 1, which is just another way of saying that the source symbol number has to be odd. So we have an even number of symbols here, so we just need to add one dummy symbol, just label it dummy with probability 0, and that should be good enough. So we just continue as before, but since this is radix 3, we just merge 3 at a time. We look at the 3 bottommost symbols here, and we merge them. And if we do that, we're going to get 0.2. So it should kind of end up around here. Oops, around here in the next column. So I'm just going to draw the 0.2 here, and just merge them all in. And the other symbols, we didn't touch them. We're just going to put them as is in the next column in the correct order. And we repeat. So we look at the bottom 3 again, combine them, we're going to get 0.4, and that should go on the top over here. So I'm going to put a 0.4 here, merge them all in, and just chuck the untouched ones back as is. And finally, we ended up with 3 symbols. that was only possible because we added this dummy over here. So we just combine all of them, we're going to get 1, and that's it. And finally, to get the actual code words, we just do a similar thing as before. We label the branches 0, 1, and 2, so like have them like depending on like the radix going down each branch. And just read like, to get the code word for say code S1, we just do the same thing as before. Look at the path from the source symbol to the ending 1 node here, and just see which numbers it are crossed. So we actually have to go backwards, as I said before. It's going to be 1, nothing, nothing. So the first code word is going to be just 1. For the second one, the path is like that. Yeah. So it's going to be 2, nothing, nothing. For the third symbol, the path looks like this. So it's going to be 0, 1, nothing. For the fourth one, it's going to be like that. So 0, 0, 2, nothing. So just 0, 2. Fifth symbol, the path looks like that. So 0, 0, 0, 0. And for the sixth symbol, it's going to be this. So 0, 0, 1. And there we have it. We can ignore the dummy because that wasn't part of the original source. But yeah, that's all your code words over here. Hopefully that made sense. Yeah, that's exactly what happened. And okay, if we wanted to find the average code word length, we can actually just use Knuth's theorem again. It works for any radix. We still just look at these circle nodes over here, the probabilities that arise from merging symbols. So the average code word length here is going to be 1 plus, well, let's just go from left to right, 0.2 plus 0.4 plus 1, which is 1.6. Yeah, just look at these, the merged ones. Yeah, and okay, it should be good. Yeah, so here's a new concept. Yeah, I'll try to motivate this based on like a small example. So in some scenarios, given some sources, compressing symbols is actually not possible. Like you can't, like what I mean by that is like you can't end up with a better average code of length compared to like the fixed length codes that we saw before that don't account for the probabilities at all. And for example, if we have a source with just 2 symbols, no matter what their probabilities are, we're going to assign the code words 0 and 1. And that results in an average length of 1. And that's just like, what's the point of knowing the probabilities then? It's just the same thing as the fixed length codes in the previous section. So one way to improve on this is to actually encode multiple symbols at a time instead of just 1. So let me just give you a definition first. If we have a source, S, with Q symbols, and they have probabilities P1 to PQ, we say the nth extension of S is just the Cartesian product S to the n. And that's just going to be all strings of n symbols in S. So like for example, if our source is like A, B, then S squared would be the source with like AA, AB, BA, and BB. The probability of each symbol in this nth extension is just the product of the probabilities of the constituent symbols in each of the new symbols. And we also order the new symbols in a non-increasing probability, just as before. So yeah, as I said, here's an example. If we have A and B as the only source symbols, if they have probability 0.7 and 0.3, then S squared is the source, or S squared, the second extension, is the source AA, AB, BA, BB, and they're going to have probabilities 0.7 times 0.7 for this one, 0.7 times 0.3 for the second one, and the third one as well. And for the last one, it's going to be 0.3 times 0.3, because probability of B is 0.3. So trust me on this, but if you run Huffman's algorithm, the binary one, on the second extension, you'll actually see that the code words assigned for these symbols here, the two-letter symbols here, they're going to be 1, 0, 1, 0, 0, 0, and 0, 0, 1. And that's going to have an average length of 1.81 per symbol in the second extension. So for each of these two-letter symbols, they're going to be having a 1.81 average length for the code words. Now, what's so good about that? Well, thing is, each of these symbols here in the second extension, they're made up of two original symbols in the source that we started off with. So per original symbol, we actually have that the average code word length would be 1.81 divided by 2, which is 0.905, which is pretty good. That's like better than 1. So we achieve some compression this way. Okay, that was extensions. So here we move on to Markov sources. So before we get onto this, if you noticed, the reason why we were able to achieve some compression from before was because we knew the source symbol probabilities. Like we were able to take advantage of them and like reduce the average length of code words based on that. So it's kind of natural to expect that if we have even more information, like even more probability information about the source symbols, then we can do even better compression. And that's what Markov sources kind of try to exploit. And here's what it means. A Markov source is one where the probability of a symbol depends on the symbol that came before it in the message. So these are given in conditional probabilities placed together in a transition matrix called M. And this matrix, the ith column of M, is going to show the probability of each symbol occurring right after the ith source symbol. We're also given another vector called P, the equilibrium probability, where Pi is going to be the probability that Si appears at the beginning. So the probability that the ith symbol appears at the beginning. We're going to need that because for the first symbol in a message, there's no previous one to depend on. So like we can't use the transition matrix for that. And yeah, it turns out that P is an eigenvector of M. You don't really need to know that. I'll just skip over it. So here's an example. Okay, so we have a Markov matrix, a transition matrix here for the three symbols here, and this equilibrium vector. So the first column here, the first column of M, it shows that the probability of S1 occurring right after S1 is 0.3. It's like the 1th column, so it's like the conditional probabilities if the S1 came before the symbol. Yeah, so S1 after S1 is going to be 0.3, S2 after S1 is going to be 0.5, and S3 after S1 is going to be 0.2. And similar for the other columns. For P, the probability of S1 being the first letter of the message is going to be 56 on 145, and so on for the other two symbols. So it turns out that we can actually use Huffman's algorithm multiple times to take advantage of these Markov sources. So before we get onto that, we need some definition. If we let S be the Markov source with transition matrix M and equilibrium P, then we say Huff E is going to be the binary Huffman code on the equilibrium probabilities. Huff I for I equals 1 to N, 1 to Q, it's going to be the binary Huffman code on the ith column of M. So like just reading the ith column of M as probabilities, the Huffman code based on those probabilities. And if we do that, we get like a bunch of different Huffman codes, and we denote their average lengths as LE and L1 up to LQ. Then the average length, LM, of the entire the coding for the Markov source, we're going to approximate that with just the probabilities times the corresponding Huffman codes. So this is like the probability of the first source symbol occurring at the beginning times the average length of the Huffman code based on the probabilities of source symbols where this first source symbol is the one that came before. So it's going to be P1, L1 plus all the way up to PQ, LQ. It's not exactly equal, but it's good enough. Yeah, so to encode a message using these extra Huffman codes that we created, we encode the first symbol of the message with Huff E, and for the rest of the symbols, we encode the symbol based on the Huffman code for its previous, for the symbol that occurred previously. So for example, when you're encoding something like this, you use Huff E to encode the first symbol, S3. And since S3 comes before S1 later, we encode S1 by Huff 3, because S3 came before S1. And for this S1, we encode that with Huff 1 because S1 came before it. And for the S2, we encode it with Huff 1 again because S1 occurred before the S2. So here's a question. We have a Markov source with a transition matrix and equivalent given by M and P here. We want to construct Huffman codes for this Markov source and find its average codeword lengths. We want to encode this thing over here and decode this. So, as I said before, this is going to entail making a lot of Huffman codes. We have to make a Huffman code based on the probabilities in this P vector and also for each of these columns here. And here's what it looks like. I'm not going to actually do it. So Huff1, you just look at you just kind of label the S1, S2, S3 as like 0.6, 0.2, 0.2 as a column here. You just like merge two of them at a time because we want a binary one in this example. And that should give us some code words. Huff2, do the same thing for the second column. Huff3, do the same thing for the third column. And Huff-E, you do it for these equilibrium probabilities. Make sure that you order the probabilities in decreasing order as you go down the column. So in this case, we have the symbols S2, S1, S3 going down because the third column is the second symbol is the one that occurs the most frequently. And similarly for, actually no, these are all in the other ones are all in the correct order to begin with. So based on this, the code words that we get for each Huffman code are these over here. I'll just go through one of them. The first one, the Huff1, is going to have, well, imagine like a 0 on here and like 1 on the bottom branch. Same thing over here. S1 is going to have code word 0. The code word for the second one is going to have 1, 0. And the third code word is going to be 1, 1, 1. You do a similar thing for the other Huffman codes and you just get these three over here. I'll let you check that for yourself later. And the average lengths, we just use Knuth's theorem on each of these codes. So 1 plus 0.4, 1 plus 0.6, 1 plus 0.4, and 1 plus 11 and 20, which is these over here. So the average length for the Markov source, or the coding for the Markov source, is just the probabilities like P1 times L1 plus P2 times L2 plus P3 times L3, and that gives you 1.47. To encode S2, S1, S1, S3, you use Huff-E to encode S2. So you look at Huff-E, look at the coder for the second symbol, 0, 0. For the S1, since S2 came before, we use Huff2 to encode S1. We look at it and it's going to be 1 over here. So then, next, the other S1, since S1 came before, we use Huff1 to encode S1. So we look at the C1 over here, and that's 0. For S3, we look at Huff1 again because S1 came before S3. So Huff1, looking at it, and we use the C3 over here because that's the corresponding coder for S3. So 1, 1. So the entire encoding is just read them like from top to bottom here, 0, 0, 1, 0, 1, 1. To decode, it's sort of a similar thing. we do the same kind of greedy like decoding strategy we did for the I codes previously. And we use Huff-E to decode for the first time. So we want to get the first symbol that is encoded in this message. So we focus on Huff-E. We read until we find a code word in Huff-E. So 0, is that a code word in Huff-E? Nope. 01, is that a code word in Huff-E? Yes. And that's going to be C3, so that's going to decode into S3. Now we focus on the rest of the message here. And since S3 was the last one that we decoded, we use Huff3 to decode the second symbol. So reading from where we left off, we look at the 1, is that a code word in Huff3? No. 1, is that a code word in Huff3? Yes, and that's S3 again. So we carry on. We have this much left. We use Huff3 to decode something in here. We look at Huff3 again. We read from where we left off. 0, is that a code word? Oh yes, already. That's S2, or C2, so S2. Right now we have 1 0 left. We just use Huff2 to decode that, because S2 was the one that we decoded last. And we read that, and we read from here. We read the 1, is that a code word? Yes, that's the first one. So we decode into S1. And finally, to decode this remaining 0, we look at Huff1 because S1 came before it. And that's going to be C1 again, so S1 again. So the decoding is S3, S3, S2, S1, S1. Hopefully that's clear. Okay, that's it for Markov sources. Now we're going to talk about something like completely different. Like it's a very, very different flavor of coding called arithmetic coding. And the cool thing about this one is that it actually encodes any message into a single real number. So here's how it goes. I'll just give you some context. We have Q symbols as before, but we also need something called the stop symbol as the last one. And we again have the same probabilities as before. Not necessarily ordered this time, you don't have to assume that. And in this context, this stop symbol is kind of like self-explanatory. Every message is always going to end up with it will always end with a stop symbol. And encoding takes a bunch of steps that I won't actually just say, I'll just actually demonstrate it for you through this question. So the question is, use arithmetic coding to on the source ABC stop with probabilities 0.2, 0.4, 0.1, 0.3 to encode CAB stop and decode 0.0. We'll do the encoding first. So let me show you. We want to encode CAB stop. So the first step in arithmetic coding, you kind of draw a line from like a segment from 0 to 1 like this, and kind of like divide it into sections according to these probabilities. So like the first 0.2 of this interval is going to be corresponding to the A. The next 0.4 of this interval, so like 0.2 to 0.6, that's going to be B. The next 0.1, so 0.6 to 0.7, it's going to be C. And the remaining 0.3 of this interval, that's going to be stop. The way we encode CAB, or like encode any message like this, is that we first look at the interval corresponding to C. So like 0.6 to 0.7 over here. And just like isolate that out. And then what we want to do is that we want to kind of like rescale this back into like the 0 to 1 size. So let me try that here. Resize. Actually, I'll copy that. Copy. Yep. So what we want to do is we want to resize this interval, kind of like scale it. Oh god, okay. It's gonna get very big, but we want to scale it back to the 0, 1 size and kind of repeat from there. So like this gets kind of like, it's like zoom this in, get like 0.6 to 0.7. And we sort of do this, like we kind of maintain these proportions of the interval back on this like smaller interval. It's like we want to kind of still maintain that shape. Obviously we can't just like chuck in these 0.2, 0.6, 0.7 values here because like the scale is out of whack. So we do, like we kind of have to do some smart calculations to do that. The way we do that is, let me show you. We do that using like a table. We keep track of the start position of the current interval that we're at, and we also keep its width. And the way it works is that since the first symbol, I guess we can put symbols here. Since the first symbol was C, we chose the interval 0.6 to 0.7 over here. So the start of that is going to be 0.6 and the width of it is 0.1. It's only 0.1 wide. Okay, that's just C done. We're currently at an interval that starts from 0.6 and it's 0.1 wide. For the next symbol, we want to know what part, like what this range is. Like we know this is corresponding to ABC stop, but like for this rescale interval, we want to see like what this actually is. Like what are the boundaries of this interval here? And the way we do that is we take away the previous, for the previous interval start position, we take away the start position of the symbol in like the original interval that we made, so like 0 in this case, and we add the width of the previous interval, so like 0.1, so like this one over here, multiply by the width of the interval for A at the beginning that we had, so 0.2. So in that way, it's like we kind of shift all of this back into like, we shift all of it back like 0.6, back 0, and then plus the plus the scaled width of the interval A here. Oops. And what we get is that's 0.62, I believe. And the width of it, it's just going to be the previous width multiplied by the width of the A interval. So 0.2. That's 0.02. Yeah, so that's how it goes. For the next one, we do a similar thing. B, we look at the previous start position of the interval, so 0.62, and take away the start position of the B here, which is 0.2. Wait, sorry. Oh, okay, sorry. I made a mistake here. Let me start again. Yeah, I think I was getting a bit ahead of myself. That's kind of doing the decoding part. But yeah, the interval start would just be 0.6 minus the start position of the interval. Plus the start position of the interval of the original part, so 0, times the length, the width of the previous interval, 0.1. That gives you 0.6. The width of it is 0.1 times, like the previous width times the width of the symbol, so 0.2. That's 0.02. For the next symbol, we do the same thing. We do the previous start position plus the length of the previous, or the width of the, well, that's not the previous one, the width of the previous interval, so 0.02, times the start position of the B interval, so that's 0.2. And that gives you 0.604, and the width is the previous width times the width of the B interval, which is 0.4. That's 0.008. And finally, the stop symbol, it's going to be previous interval start position plus the previous width, so 0.008, times the width of the stop symbol interval here, so it's 0.3. And that's 0. Wait, not the width, what am I saying? The start position, so 0.7. So that's going to be 0.6096. And the width is going to be 0.008, the previous width times the width of the stop symbol, so 0.3 over here. This one. And that's 0.0024. So what we end up with is that we get like a really small interval at the end after doing all this. We're going to get an interval that starts at 0.6096 and it's 0.0024y. So it's going to end up at 0.6120. And all the encoding is just any number that you wish in this interval. So say 0.61. So that could be the encoding for CAB stop. For decoding, we sort of try to reverse this process. We still draw the interval again. Is it 0.2 for A, 0.6, 0.7, 1. And we look at, like, we kind of like stab where 0.08 would be. So like that's around like here. And for the interval that for like the sub interval that the stab lands in, we kind of zoom in on that again, like enlarge that, and kind of rescale where that stabbing was done. So like it should be around like here. We kind of like divide this enlarged interval, like rescale it back to like the original proportions as before. And again, see where the rescaled stabbing position, which should be like around here, ends up. So that's going to be like the interval B. And we kind of repeat this until where we stab is at the interval for the stop symbol. And again, we do this using another table. The table, it's going to have first column scaled encoding number. Well, let's just say number. That's just going to be like the 0.08 at the start, and then just keeps getting rescaled as we enlarge the intervals that we end up in. We're going to need the interval width as well. Actually, the actual interval, just to make it easier, and the interval width. And we're just gonna put in the resulting like decoded symbol at every step. Yeah, so what we start off with is the starting encoding number. The scale number, we just start with 0.08. That's the thing we want to decode. What interval is that in? That's over here, right? So it's gonna be in the 0 to 0.2 interval, and this interval is gonna have 0.2 width. And the decoded symbol is A because we ended up in the A subinterval. Now we want to rescale this interval that we ended up with, and also rescale the encoding number in that way. So how we do that? We take away the previous encoding number with the start position of the interval that we ended up with, so 0. And we divide by the length of that interval. That gives us 0.4. And we look at where 0.4 lies in the original subintervals. So 0.4 should be around here. So we end up in a 0.2, 0.6 range. And the interval width of this is 0.4. And the decoder symbol will be B because we ended up in the B subinterval. And we repeat. We take the previous encoding number, 0.4, take away the interval start of the previous interval, so 0.2, divide by the interval length, 0.4. And that gives you 0.5. that is again in 0.2 to 0.6 range, and that's going to be 0.4 in width, and that's going to be B as well. Next, we do the same thing, 0.5, the previous number minus the interval start, 0.2, divided by the interval length. That gives you 0.75. And now that's pretty good. I think that's the source symbol, stop symbol here. It ends up over there, like 0.7 to 1 range. Don't really need to write the interval width here, but the decoder symbol would be the stop. And the thing about arithmetic coding, we always know that messages will end up with a stop symbol, so that's where we stop. We don't continue any further. So the decoding is A, B, B, stop. Okay, so that's arithmetic coding. Yeah, there we go. You can have a read of those. So yeah, that's it for arithmetic coding. Now we're going to move on to the final topic for today, LZ78. And this is just another completely different kind of compression code as well. I think this is used for zip files maybe. I think I heard that, not too sure, but yeah, pretty interesting stuff. So how it works is that it kind of builds up a table of code words like while reading messages, and it recognizes recognizes those kind of like a prefix table in later parts of the message. And yeah, here we go. That's gonna be some text. You can read that later. I'll show you actually how to do it. So let's just say like we wanted to use LZ78 to encode this ABB, AACC, ACA, BAC, ACAA message. What we do is we start we kind of have a dictionary here, and it starts off with the 0th entry being empty, and that just means like the empty message or empty string. For the message, we try to find the biggest prefix, like the longest prefix of the message that's in our dictionary. So like, ignore this part for now. That's like the one that got created. Like the longest prefix of the message that we find in the dictionary, it's going to be the empty string, right? Because there's like no other, there's no other shorter, there's no other prefix that's in D. So yeah, the longest prefix that we find is the empty string. And when we find that, we kind of output 0A to signify that we extended the 0th entry by A to create a new entry A here, 1A. Next, we kind of ignore the A now. We already dealt with that. And we try to find the longest prefix in this remaining message that's inside this dictionary. And again, that's going to be the empty string. It's not going to be A because A is not a prefix. It's going to have to be the empty string again. So what will happen is that the prefix that we found is B, is the empty string. We output 0B to signify that we extended that longest prefix by B to get to this point here. And we record that new thing as the new, a second entry here. And we continue. So we ignore this B for now, since we dealt with it. For this remaining part of the message, we again ask the question, what is the biggest prefix of this message that's inside this dictionary? Well, this time it's not the empty string anymore. It's going to be B. The longest prefix out of these in this message in the dictionary is going to be B. So what happens here is that we kind of look at the letter right after the prefix that we found, chuck that in the dictionary, and output 2A just to say that we extended the second entry by A and put that into a new dictionary entry. Again, we kind of repeat that. The next one is going to be right, okay, there's a typo here. Let's just skip that part for now. For this part, we find a C. That's going to be there's no prefix in the dictionary that has that's going to be there's nothing in the dictionary that's a prefix of this message here, except for the empty string. So again, we extend the empty string by C to create a new entry. For the next one, ACA. Yeah, okay, this is meant to be an AC. Sorry about that. But yeah, imagine that this is an AC, and the fourth entry is an AC. We see AC as the longest prefix that's in the dictionary. So we look at the one after, so ACA, chuck that in the dictionary, and say that we extended the fourth entry by A. Because yeah, just imagine the fourth entry is AC. There's a typo from the third step to the fourth step. And we'll just continue that kind of thing, just like making new dictionary entries as we go, until we run out of the whole message. And the encoding, if you ask, is just like the outputs that we had, just like strung together in one big line here. It's like 0A, 0B, 2A, 1C, 0A, 0C, 4A, 3C, 6A. Now to decode this, we kind of reverse the encoding process, where we kind of rebuild the dictionary entries based on the outputs that we got. So when we want to decode something like this, we again start off with an empty dictionary entry, because like we know when we were encoding, we had the empty string first. When we see the 0B, we say that like we want to this pair is kind of telling us that we extended the 0th entry by B. So we kind of put that B in here as a new entry and output that B. For the second one here, the second pair, it tells us that we extended the 0th entry by A, so we put that extension here, that's just A, and output A as well. And same thing for C, pretty boring for now. But when we get to 2B, this is saying that we extended the second entry by B. So we had AB as a new entry, and we output that. For the next one, 1C, we extended the first one by C. So we put that in the dictionary, and we output that BC, like the extension. 5B, that's saying we extended BC with a B, so we get BCB, we output that. For C, again, we extended the fourth one by C, so we get ABC, we output that. For the last one, we extended the sixth one by A, so BCBA, and we output that. And the decoded message is just then the outputs just put together in a one big string. So BAC, AB, BC, BCB, ABC, BCBA. And yeah, that's actually it for chapter 3. Part 2 is on Wednesday. That will cover chapters 4 to 7. Sorry about going over time for this one. But yeah, I'll see